We've all been there before. The chemistry gods have reached down and demanded that you model something important. Yesterday it was benzene. The day before that it was the structure for morphine. Today it's come up with a reasonable structure featuring an intermolecular hydrogen bond between two water molecules, the famed water dimer. Now, if you know anything about computational chemistry, you'll understand that part of the frustration lies in trying to figure out what combinations of software, theory, and basis sets to use to get this calculation done correctly. You might think that the right idea is to talk to a computational chemist. Sure, might be the right thing to do. The problem with this strategy is that it depends to whom you are talking. For example, Team Hybrid Functional might recommend that you do something like use a B3LYP calculation or the ever popular M062X, we call it the Minnesota approach. Sure, doing so might give you a fairly reliable result, but the speed of the calculation truly depends on the speed of your machine. Team Wave Functional might suggest using a heavy-hitting theory like MP2 or CCSD parentheses T, the gold standard of modern computational chemistry. Sure, you may need to build a supercomputer to get the calculation done in a reasonable amount of time, but the resulting structure and data will be really good. I mean, really good. Remember, all you are trying to do is to get a quick and reliable answer. The issue ultimately boils down to using the right computational tool. There's some good news. There is a way to attain this outcome. Have you ever tried semi-empirical methods? I know. Some of you might have actually just thrown up in your mouth a little bit, but maybe we don't need an answer that's accurate to 4 decimal places. Maybe what you need is a good starting point for a future heavy-hitting calculation like an M062X or an MP2. In that case, semi-empirical methods might be right for you. Additionally, semi-empirical methods are usually very fast. A small system like the water dimer can easily converge in less than 2 seconds for a semi-empirical calculation, but may take as long as 2 hours for other popular theories. Semi-empirical methods show up in many popular software packages. These include free packages like Orca and games, or proprietary packages like Spartan or Schrodinger. For this exercise, we'll be using MOPAC, which is an open source software package that centers on semi-empirical computational methods. Let's look closely at the chemistry for a moment. When you carefully research the water dimer structure, you will find that it's commonly represented like this. See how the O, H, and O atoms are in a straight line? A reasonable computational method will successfully recreate this structure. Now, if you dig a little bit deeper into the chemistry, you'll find that there are a few well-established characteristics about the water dimer. For example, it is known that the accepted oxygen-oxygen internuclear distance in the water dimer is 2.98 angstroms, this value up here. Another known is that the binding energy, this is the energy released when 2 or more molecules come together, is 3.16 kilocalories per mole. That's that value that's right here. So, a reasonable semi-empirical calculation should generate a structure with similar internuclear distances and energetic data. MOPAC calculations, the ones that we're going to do for this video, are typically quite easy to perform in a program called WebMO. It's important to know that WebMO does not do the calculation for you. You can think about WebMO as sort of being like the car without the engine. It's just an interface that you can use to build and prepare molecules for doing formal calculations. When you're ready to calculate in WebMO, the software lets you pick which computational engine you want to use. Let's take a look at a calculation in MOPAC using WebMO. So I'm on the WebMO demo server right now, and I have preloaded the water dimer into this system here, and I've actually even cleaned this up using this little icon, this dustpan icon here to the far left-hand side. This is a comprehensive cleanup using an ideal geometry, or an idealized geometry here. You notice this little dashed line right here. This represents a hydrogen bond, so we can actually, pretty easy to do, we can remove that. We can change it to a single bond if we want to. That's not what we're trying to do, but we can actually remove that if we want to. If we want to put it back in, we just click and drag from the hydrogen to the oxygen, and boom, there's your hydrogen bond. Now, the hydrogen bond doesn't matter in this particular case because MOPAC isn't going to really read that. It just helps WebMO get you a reasonable pre-optimized structure before you do the actual formal calculation. So it kind of helps kind of speed up the calculation and the reliability in the calculation here. All right, so once this thing is ready to go, lower right-hand corner, we're going to pick our computational engine and see here that this is already selected for MOPAC. This is a semi-empirical calculation is what we're talking about here. But we're going to go ahead and move forward on this. We're going to configure our MOPAC job option. So this will pre-populate with a name. Let's go ahead and just name it. We'll call it water dimer. And the calculation that we're going to do here in this case is we're going to do a geometry optimization. And I know you computational people, why don't you do vibrational frequencies too to make sure there's no imaginary frequencies? Because I like to live dangerously. That's why. Let's just go with a geometry optimization. I know that's the sloppier way to do it. But let's just go ahead and do a quick geometry optimization. We're setting the charge to 0, and this will be a singlet. All right, on the job manager screen, once the job is submitted, here's right here. So here's our molecule. Go ahead and open this thing up. There's our optimized structure. Ooh, this is ugly looking, isn't it? That's not a very good structure at all. It's a big hint about PM6 right there. All right, so here's the thing to note. What just happened when we sent this forward to do an optimization? This is a kind of the interesting part. Geometry sequence energies right here. If you click the little film strip that's right here, you can animate it and kind of see what ended up happening. So it actually animates step by step and shows you how the system twisted until it ultimately got to a point where it was fairly low in energy. Now, another fascinating aspect of this too is if you actually take a look at the energy as a function of each one of these steps, what you'll see is that this is our input structure right here. So we're plotting energy as a function of steps. This is the energy of the input, the structure we put in initially. It adjusts slightly and drops, lowers in energy here. By about the 95th step, there's an adjustment that happens where the energy lowers even further, and then eventually gets to a minimum point right here where the calculation effectively converges. So you can see from the demonstration that there's actually several different types of theories that you can use when you do a MOPAC calculation in WebMO. Chemists oftentimes call these theories Hamiltonians. They're essentially instructions on how to calculate these chemical structures. Many novice computational chemists are initially troubled over which Hamiltonian will work best for their needs. I mean, think about it here. You start, you log into your demo server at WebMO, you build your molecule, you select, you want to do a MOPAC calculation, you get to the configure job options screen, you're selecting your theory and look at all these different theories. It's like, oh my gosh, what do you do? Which one do you pick? In this video, we are going to evaluate a few Hamiltonians to determine which gives us a reasonable structure. That is, one that's going to match the accepted values for the water dimer. Our method will involve a couple of key steps. So first, we're going to build an initial model based on the bond line structure that we want to emulate, this guy right over here. Remember, WebMO lets you draw a hydrogen bond between the two molecules. And although the hydrogen bond isn't really important to MOPAC, while you're pre-optimizing in WebMO, the hydrogen bond will help keep the structure together so you don't end up with these really crazy looking geometries or anything like that. I've provided the Cartesian coordinates for this pre-optimized structure in the comments below. Next, we'll have MOPAC optimize the dimer geometry with several different Hamiltonian. I picked a few of the classic forms, so things like AM1, PM3, but then I've put some of the more newer ones in here like PM6, PM6 DH+, PM6 ORG, this is a really new one right here, and then my favorite PM7. Then, once we've done our calculation here, just because we need to calculate out the binding energy, we'll have MOPAC optimize the structure for individual water molecules using each of these Hamiltonians. Just a quick word of caution though, MOPAC prints formation enthalpies and not electronic energies. So when you do the calculation, instead of getting electronic energy that comes out of this, you see this a lot in other programs like Gaussian, instead you get formation enthalpies. These quantities are technically different, but in this example, we're going to assume that they're fairly comparable with each other. Once all of our data is collected, we will calculate. Then we'll assess the results. Are you ready? Here we're looking at semi-empirically optimized water dimer structures. Now, out of the 6 Hamiltonians that we evaluated, PM3, the PM6DH, and the PM7 Hamiltonians gave a qualitatively reasonable result. The other 3, not so linear. I would call them angled. So they're not going to be very helpful for this particular system that we're evaluating right now. What about the oxygen-oxygen bond lengths? So remember, the accepted value is 2.98 angstroms. Almost all of these methods tend to underestimate the oxygen-oxygen bond length. How do you know that? Look at the error. Now, if we draw the dividing line at 10% relative error, we can see that PM3, PM6, DH+, and then PM6 ORG and PM7 all fall beneath that 10% error. In other words, they're giving you reasonable oxygen-oxygen bond lengths. Now, when we consider binding energies, a couple of interesting things emerged. First, the accepted heat of formation for water in the gas phase, and that's courtesy of our friends at the National Institute of Standards and Technologies here in the US, they report a value of negative 57.80 kcal per mole. Take a look at the PM7 calculation right here. So this number, if we're just talking about just a single water molecule itself, this matches accepted values pretty well. That's pretty cool right there. Not necessarily relevant to what it is that we're dealing with here in this case, but still pretty interesting. Second, look at the errors. They're all positive values. This is showing that all 6 Hamiltonians overestimate the binding energy values. Third, if we look at the relative errors and we draw the line at 30% relative error, only PM3 and PM7 fall within this threshold. They seem to produce the most reasonable binding energies. And they're not fantastic, but they're the most reasonable out of the 6 that we took a look at. So let's do a quick summary comparison. The true stars for the example that we're examining here are PM3, PM6 DH+, and PM7. The other 3, AM1, PM6, and PM6 ORG, they have some shape issues, so they may not be all too reliable. In our example, the PM3 Hamiltonian gave the best overall results, but the bond lengths tended to be slightly exaggerated. PM7 was also a good candidate, but the PM7 energetics were fairly unreliable. So that aspect might be important if you need that type of data. Totally not related to this whatsoever. I love the PM7 Hamiltonian. I really need to make a t-shirt that says MOPAC PM7 on it, and I would wear that baby around in public with pride. I love PM7. Holy cow. I can't tell you how much I love that. All right. Sorry. Sidetrack. Had nothing to do with what we were talking about. Finally, using the PM6 DH plus Hamiltonian gave some pretty good results, but again, the energetics weren't very good. Here's the bottom line. If you need to model a semi-empirical intermolecular hydrogen bond, I encourage you to try PM3 or PM7 first. PM6 DH plus is also a good alternative. These approaches will ensure that you get a reasonable structure for these types of systems.